Today let's try to solve this problem called minimum inversion count in subarrays of fixed length. So you are given an integer array nums of length n and in integer k, and inversion is a pair of indexes ij from nums such that I is less than j and nums I is greater than nums j. The inversion count of a subarray is the number of inversions within it. Return the minimum inversion count among all subarrays of nums with length k. So the first example, nums is this 3, 1, 2, 5, 4, and k is 3. The output is 0 because we consider all subarray with length equals 3. So basically, we can start from this one. This subarray, which is the first one, we have two inversions, 0, 1, and 0, 2. Mainly it's like 3, this one, 3, and then 1, and then 3, 2. And then, but if we move the subarray one position to the right, we have this 1, 2, 5, and it has 0 inversion because, as you can see, the array is sorted. And we can also consider this 2, 5, 4. It has 1 inversion, so it's 1, 2. But actually in this case, as soon as we reach here, we got 0, we can terminate the program because there's no way it can get better than 0. But anyway, we can still consider this window 254. 254, you can see there's 1 inversion, which comes from this 5 and 4. So because there are like 3 options, like the lowest value among the 3 options is 0. That's why we return 0 as the final answer. So yeah, that's pretty much all for the problem description. And let's think about how can we actually solve the problem. To solve this problem, we're going to look at this example again. So the nums is 3, 1, 2, 5, 4, and k is equals 3. So mainly we should find all subarrays with size 3. So what can we do here? Let's try to add the elements one by one. So let's assume that we are going from left to right. And we also want to keep track of the current inversion count. And when we try to add 3, and what will be the inversion count? Because there's only one element, there's no way for it to have any inversion. So we just remain at 0. And then we're going to try to add 1. So 1, well, at this point, how should we update this inversion count? So if you, with our naked eye, we can tell that there's 1 inversion because 3 is larger than 1, and this is on the left hand side. So in general, like for example, there's like 7, 9, 10. We're trying to add 1 here, for example, presumably, and actually there will be like all 4 of this can be paired with 1, and that would be an inversion pair. So because these numbers appeared before, but at the same time larger than the numbers that we're trying to edit now, because the way that we iterate the numbers from left to right, that's why it violates the inversion, or that's why we have this inversion pair. Okay, let's get back to the original state here. So the more formal way to like formulate what I just said is that when adding numbers I, we want to know how many elements that are larger than, well, I might call strictly larger than, because if it is equal, it doesn't make an inversion. So how many elements that are strictly larger than num_i? And that number will be added to the inversion count, here. So in this case, we're adding 1. There's only one element that is larger than 1, which is 3. So in here, we just add 1. And let's try to move to here. And we're going to ask the same question again. How many elements that are strictly larger than num_i that appeared before? Well, that appeared before. So here, 1 is not greater than 2, and 3 is greater than 2. So that's why we should add 1 as well. So 1 plus 1 will be 2. And then we're going to move here. And then this 5, we're going to ask the same question again. But before we do that, we are essentially looking at numbers here. Because the windows right now is 4 size now. So we want to pop this 3 out, basically. So, so that's what we're doing here. Whenever we reach an element that has greater than k sized, we want to pop the leftmost element. So in this case, we are adding 5, and we can no longer consider 3, because if we consider 3, then we will be considering this window. So that's why we have to pop 3. And when we go to this 4, we have to pop 1. So that's the next question you want to answer. When removing num_i, which is the leftmost element, right now I'm trying to remove 3. And what should we do to remove 3? Well, let's think about it. Whenever we try to move something, it's always going to be the leftmost element. So if it is the leftmost element, then what elements here can make an inversion that this number takes part in? Well, the answer is we need to know how many elements that are strictly smaller, right? Is it smaller? Yes, it is smaller. I confused myself. Anyway, let's move on. Num_i that appeared after. So we want to know how many elements that are strictly smaller. So here in this case, we can see there's 2 elements that is smaller. So that's why the current inversion count should -2. So it will be 0. Because we know that the elements after num_i should always be larger or equal to num_i. But the fact that these 2 numbers are smaller and strictly smaller, that means that these numbers can match with this number that we're trying to remove, and that would make us an inversion pair. Okay. So after that's done, we can move our pointer to here. And we can answer the same thing again. Now we are trying to add nums I, and we ask this question again, where nums I will be 5 here. How many elements that are strictly larger than nums I that appeared before? I mean, in this window. So there's going to be like 0. So because there's no element that are strictly larger than 5 here. So the inversion count remains 0. And every time we finish adding one element, and as soon as this I index is larger or equal to k minus 1, it means that we have at least k considered k element, because if we're just looking at this element, we cannot consider that as an answer, because we are only considered these two elements that will not be large enough for k equals 3. So anyway, we're going back to here. Because we don't have to add anything, because nothing is larger than 5. So 0 plus 0 will be still 0, and 0 will be part of our answer. And basically, we just keep doing that. For the last element, we do again 4. And then we're gonna ask the same thing again. Well, before answering this question, we have to remove this element 1. We need to know how many elements that are strictly smaller than nums I. Again, because these windows right now we're seeing has a length of 4. We have to shrink it to a length of 3. So if we want to remove that, we're going to answer this question. How many elements that are strictly smaller than nums I that appeared after? Well, the result is 0. Because 1 is smaller than all of these. So we're going to move that here and here. But that's not the end, because we still need to consider 4. So how many numbers that are strictly greater than nums I? So in this case, there is 1. 5 is strictly larger than 4. That's why the current inversion count is 1. So because like previously we have seen this 1 to 5 that has an answer 0, so that's why at the end we just return the answer is 0. Yeah, that's pretty much how we're gonna solve this problem. And the main question is answering this. How many elements that are strictly larger than nums I that appeared before? So, well, if we formulate the question in this way, there's a very useful data structure called binary index tree, or somebody call it Fenwick tree. So basically, this, when adding nums I, we want to ask how many elements that are strictly larger than nums I. That is basically like trees of range query, because we want to know the thing that are strictly larger than nums I, so it will be nums I plus 1, and this one, the boundary will be the maximum value of the tree. And for removing, it's going to be something very similar, because we want to know our count that are strictly smaller than nums I, and this will be like range query of so this will be the smallest element, and then also nums I minus 1. And all these, this is log n, and this is also log n. and we need to update the frequency of each number. See, when we try to add something, we just do like tree update num_i to like tree query num_i +1, something like that. And when we're removing something, it will just -1. And this is log n as well. Log n. This is O log n. So as you can see, we just maintain like a 2-pointer and also do this O log n operation. So the total time complexity will be O n log n. And that's pretty much how we're going to solve the problem. And let's take a look how can we actually implement the solution. Okay, so let's start with the implementation. First thing we're going to do is that we're going to create a Fenwick tree. As we mentioned before, we're going to need a Fenwick tree to calculate the range sum so we can solve this problem more easily. So I'm going to define a name here, Fenwick tree. This is public. And we need a factor to store values. And then we need a constructor. And values equals to factor and n+1 because the indexes will going from 1 to n, so 0 won't be used. Initialize all the value as 0. And we need this low bit helper method. This low bit helper method basically will get the least significant bit of x. So for example, the input is like x equals to, in binary, equal to 110, 100, and this will return 0001, 00. Yeah, so this is because this turn on bit is the least significant like on bit. That makes sense. Okay, so that's it. And to do that, we use some binary operator, x -1, and then update. We'll take this value. And actually, let's start with the query. This query line. This will return sum between 1 all the way to I. So answer equals 0 while I greater than 0, and then answer plus equals to values I, and then I minus equals to low bit. We remove the least significant bit, and then finally just return answer. And then after we have the query, if we want to, so this one is basically update nums, like nums I to value, basically. That's what we want to do. So because the way that the Fenwick tree is constructed, we cannot just do nums I equal value. We need to update all its parent nook as well. So again, we're going to do something very similar to query here. But first, we need to know the delta we're going to update. The delta is basically the new value minus the current value, query I minus query I minus 1. This one is to get the current value, and this one is the new value. Value minus the so this new value minus the current value will be the delta. And then we need to pass down the delta to all the parent node, basically. Let me just put down here. While I is less than values of sized values plus equal delta, and then I plus equals a little bit I. And after that's done, we need to create some helper method. For example, we want to query not just I all the way to 1, but also any ij. So we can make use of the helper method here, query. So this is exactly like prefix sum. Just query j minus query I minus 1. And I'm going to create one more helper method just to make the code more concise. If we only query one element, then it's just query I query I minus 1. Yeah. Okay. So after that's done, we can start coding our problem. But before that, you can see this here, the Fenwick tree here actually takes the integer n. So, but here the number of value can go up to 10 to the power of 9. So we basically need to normalize the value first. So what we're going to do is we need to create another helper method to help us normalize the array. So basically, what I'm trying to say is that this, for example, this could be really large. Let's say it's 10 to the power of 9, and then 2, 3. I want to convert this thing to the rank of each number, because if you think about it, I don't really need the actual value. I just need to know the relative order or rank so that I can calculate the inversion. So, so I can just do something like 3, and then this one will be 1, and this one will be 2. So this 3 means that the rank of this 10 to the power of 9 originally will be 3, like, because this is the biggest value, and this 2 will be the smallest, so the rank will be 1, so on and so forth. So we don't have to handle this really large number. But in order to do that, we need to create a helper method. I just call it normalized. Basically, just turn the value. Hold on, I need to finish the typing first. So basically, this one is just turn values into ranks. That's what we're gonna do. So we need n sized, and then vector rest sized. Well, actually, we can use n here, and then vector sorted. We need a sorted version of that, and this one will be sorted, and then we should sort the sorted n, and then we need a rank of. So rank of x will be the rank of element x in the original nums. Okay, so we're gonna fill in this map now for I equals 0, I less than n, plus plus. So we only want to consider that if there's no rank for this value yet. So it means that if there's repeating elements in this sorted array, we just take the first one, because it doesn't make sense for the same element to have different rank. So we just need to +1, because we need to do +1 here, because the way that Fenwick tree works is we just gonna keep using this low bit. If we use the index 0, the 0 actually don't have any turn on bit, so this won't work. It will just give us an infinite loop. So that's why whenever we use Fenwick tree, we need to start at least 1. So but this rank can, you may say it can start at I, but if we start at like 0, it will be a problem for using the Fenwick tree later. So I'll just add I +1 here to make sure the index is at least 1. Okay. So let's go on. After we have this rank off, and then we're just gonna fill the final result. So the result I will be the rank of this number I instead of the actual value. And then finally, we're just gonna return result. Okay. So after this helper method is done, then we can finally start coding the actual problem. So again, I'm gonna initialize the dimension. And then we want to normalize the factor or the input array, and then we want to create a Fenwick tree. A Fenwick tree, new Fenwick tree, n +1. Just n +1, just for safe. I think it works for n as well, but I just want to add n +1 just for safety measure. So long answer equals to, well, at the beginning, I just going to initialize at the very large value. So long current is the current, this is the current inversion count. And then I'm going to add the element 1 by 1 to update the current inversion count. For r equals 0, r less than n, r minus minus. And then if r minus k is greater or equal to 0, that means that we need to pop the leftmost, which is numst r minus k, just to keep the whole sliding window within the size limit of k. So how can we do that? Again, like we need to, well, what do we need to update for the current inversion count? If you still remember, we need to consider anything that is strictly smaller than nums r minus k, because nums r minus k is the leftmost element. Now we are trying to remove that. So assume that this Fenwick tree contains all the elements inside the current window. So if we want to remove this leftmost element, so anything that is strictly smaller than the leftmost element can create an inversion. So that's why, because we are removing it now, and then the inversion count will actually minus equal, because originally this nums r minus k and or this order compare with all the numbers that is strictly smaller than itself and create an inversion. Now that it's gone, then we can retrieve back the inversion count. So this is just the way range carry, just to get like anything that is strictly smaller than I minus k minus 1. Remember here, nums r minus k is no longer the actual value, it's the rank, and then this one is the first one as well. So we're going to count every number, how many numbers between the first rank all the way to nums r minus k, which is the thing that we're going to remove minus 1. So it's going to be strictly smaller than the value that we're trying to remove. Okay. And then after that's done, we need to update our Fenwick tree as well, because the Fenwick tree is supposed to contain only the element that is inside the window. Now we are popping that thing out. We're going to update. We're going to minus the r minus k. So this one, the frequency, we need to minus that by 1. Range carry nums r minus k minus 1. Okay. And then now that this is for popping out the leftmost, this is for adding nums I into the tree. So if we want to add that to the tree, what can we do to update the inversion count correctly? So similarly, now because this nums R will be the greatest indexed for all the numbers that we have considered so far, because we're going from left to right, right? Every index that we have considered before is going to have a strictly less index. I'm not talking about value, I'm talking about the index. So for any smaller index, if the numbers are larger, so that would create an inversion between that value and nums R. So that's why when we are trying to consider this nums R, we need to basically consider anything that is strictly larger than nums R. Okay, this is one range. We can do that. Range carry 1. Sorry, it's not 1. It's nums R plus 1, and then so again, this nums R is a rank. So I'm going to find this rank plus 1 all the way to the maximum rank. So I just want to know how many numbers existing in the tree right now, and because all of them can make an inversion pair with nums R. And then after that, we want to add the nums R into the tree. So actually the comment may be better to put here, add nums R to the tree. Tree update nums R tree range carry, and then nums R plus 1. Just because you just add one more value to this rank. And here's what we're gonna update the answer. We can just we cannot just do this answer per, because what if we only consider one element or two elements? We need to make sure the window is at least as large as k. So that's what we're gonna do. If this is at least k minus 1, the index is at least k minus 1, then it means that the window is at least as large as k size. So then we can consider the answer of the current window. And finally, we can just return the answer. Okay. That's pretty much all. Let's try to see if it works. Okay, there's missing class. Okay, missing semicolon. Let's try that again. Okay, try submit. Okay, accepted. So the time complexity, again, I think I mentioned before, I'm just going to mention it one more time, is going to be n log n, because each time when we do this range period, it's going to take log n time, and we're going to do it n times. So totally going to be n log n, and for the space, it's going to be O n, because mainly we just use this. We just use the let me see, the Fenwick tree implementation requires size n storage, and also when we do normalize, we need to create an extra array as well. Yeah, so that's pretty much all, and thanks for watching. I will see you next time. Bye.